Great, thank you very much. It's oh, fantastic to be able to talk to you all this morning. I was really thrilled to see everyone put their cameras on so I can see some faces after so long. It's obviously a shame that we can't be together, but I hope that everyone's doing okay and managing well and coping all right with the ongoing situation. So this morning I wanted to take the opportunity to talk about some work that is of great interest to me, that I've been working on with Julia Talman and Gerardo Valori, but it's heavily based on the work led by Etienne Pariat in Paris. And I also want to say right at the start that this is kind of preliminary work. So it's very much a work in progress. And that's kind of why I wanted to talk about it this morning, give it a bit of an airing, have discussion, hear people's viewpoints. But it links into the topic of coronal mass ejections and magnetic helicity. So just by way of an introduction, I'm sure everybody on this call, on this seminar, knows the sun in detail and knows about different forms of solar activity. But just in case, we have one form of solar activity that we call a solar flare, and there's an AIA movie on the left-hand side showing a confined solar flare, during which time a region of the plasma in the sun's atmosphere is being heated to tens of megakelvin and radiating very strongly in certain wavelengths. But the kind of activity I'll be talking about this morning are the eruptions of magnetized plasma from the sun, the so-called coronal mass ejections. And they are the form of solar activity that I've been interested in for quite some time now. I find them scientifically interesting, but also very beautiful as well. So they kind of tick these two boxes for me. And then when it comes to motivations for studying coronal mass ejections, we very much want to know the physical processes behind these eruptions. So, you know, the mass of a mountain ejected into space at up to speeds of up to a few thousand kilometers a second, what is happening in these events? And despite the fact that they were first discovered in the early 1970s, we've still got lots of open questions about the physics that underlie these vast eruptions from the sun's atmosphere. But then there's another aspect to coronal mass ejections and our motivations for studying them, and that comes down to space weather. So coronal mass ejections are the drivers of severe space weather at the Earth, and there is an aim in space weather forecasting to be able to both accurately forecast their arrival time at the Earth, but also achieve a sufficiently long lead time to that forecasting. So the forecasts need to be useful, and certain industries will need perhaps several days forecasting lead time to know that a coronal mass ejection is headed our way and when it's going to arrive at the Earth. And these two kind of sets of motivations are the threads that run through this piece of work, because we want to be able to kind of tick both of these boxes, carry out research that helps us understand why coronal mass ejections take place, but then use that knowledge to also work out when the corona is likely to become eruptive before we actually see the eruption take place. So just very briefly, a lot of the sort of work that I've been interested in over recent years comes down to the physical processes that are taking place in the hours and days before a coronal mass ejection takes place. So the time during which energy is being built up in the corona that is then released during the eruption itself. And I'm very much interested in what are the photospheric processes that are taking place, or the drivers in the photosphere that are priming the corona. And so I've just sort of picked out three different kinds of evolution that the photosphere can go through that we see happening before a coronal mass ejection. So the first one relates to the work done by Alex James, who has been looking at the photospheric flows of orbiting motions of like polarity fragments. So this movie here shows a sunspot region, and in the leading polarity, you can see the fragments of the sunspots coming together, but orbiting around each other. And through studying different active regions which exhibit this particular evolutionary sequence, Alex has found that these photospheric flows can drive reconnection in the corona and form what we call a magnetic flux rope. And he backed that up by a nonlinear force-free field extrapolation of this particular region, which found indeed a right-handed twisted flux rope that's shown on the top right-hand side of this slide. So you can see in the blue and red lines the twisted nature of the flux rope. And what's also interesting and important about this particular flux rope is that its underside is located in the corona, in the low plasma beta environment of the corona. And so if you took a cross section of the flux rope, you could visualize that. This is very schematic now on the bottom right hand side in a figure that Bernard Klein gave me, where you would see the kind of body of the flux rope and then overlying field lines and an X line running under the flux rope and then loops below that. So this gets called a HFT configuration flux rope or hyperbolic flux tube rope. And it's interesting because if you perturb this magnetic field configuration, the X line could collapse down into a current sheet and you could get reconnection. So the physical processes, the photospheric flows in this region that built the flux rope tell us about how the photosphere is evolving and then driving reconnection in the corona that's building a flux rope that in this case and the other cases that Alex looked at then erupted as a coronal mass ejection. So then a second kind of physical process that we see in the lead time running up to a coronal mass ejection gets called flux cancellation. So there's a paper by Ard van Balhoy and Pete Martins back in 1989. And for those of you who've seen me talk before, I think this is a really important and relevant model for the sun. And there's a schematic in the paper that shows how magnetic field in the corona can be evolved by shearing and converging photospheric flows that then drive reconnection low in the atmosphere and build up a flux rope, which is shown in the last panel on that top, on the top right hand side of the slide. In the photosphere, the name flux cancellation is given because in the photospheric magnetic field, you see the convergence of opposite polarities, and along that central inversion line, you see the coming together of the white and the black, the positive and the negative, and it disappears. So that gave this, this phenomenon the name flux cancellation. In reality, what's happening though is reconnection in the lower atmospheres, reconfiguring the field. Very small loops get formed along the inversion line and they then get submerged by magnetic tension down through the photosphere. So they disappear from the layer in which the magnetic field measurement is being made. But this is another photospheric evolutionary sequence that is related to flux rope formation. But because flux ropes are forming by reconnection low in the atmosphere, you end up with a flux rope that if you took the cross section, you would see its underside being located down in the photosphere chromospheric layer where the plasma beta is high. So these flux ropes have a different specific configuration and they get called bald patch separatrix flux ropes because of the concave up magnetic field lines that reach down to the lower atmosphere. So that's the second kind of evolutionary sequence by which you can build a flux rope that then erupts. And then as a third example of photospheric flows, there's been a lot of work around shearing motions, so consistent shearing motions acting on the coronal field. And then in this scenario that I've shown, this is a figure from one of the breakout model papers. So there's a series of papers by Spirangiakos, McNeice, Lynch, who've all looked at the modelling side of this particular evolutionary sequence in the photosphere. And so in this scenario, if you have a central arcade that's shown in blue and you shear the foot points of that central arcade, you are energizing it, and breakout reconnection happens above it, removing overlying field and the tension associated with that, and allowing that blue central core to explosively erupt due to reconnection. So these are just 3 examples of physical processes that take place in the run-up to coronal mass ejections. And they sometimes get called trigger processes. And collectively, trigger processes or trigger mechanisms relate to the processes that bring the magnetic field to the point at which it can erupt as a coronal mass ejection. In fact, though, there have been over the years many trigger mechanisms proposed by the community. So this is a table put together by Tibor Turek that summarises that. We've got the trigger mechanism and then some of the references associated with that. So this table is just a way of illustrating that when we study the corona, the photosphere, in the run-up to a coronal mass ejection, many different processes can be happening, and they're captured here in these modelling mostly papers. So there could be sunspot rotation, there could be twisting of field overlying the eruptive structure, there could be converging flows, flux cancellation, flux dispersion, flux emergence, helical kink instability, a whole list. So this is here really just to force the point that when it comes to those hours and days before the coronal mass ejection, we see different processes taking place. But when it comes to the eruption itself, the community who use the phrase trigger mechanisms then use the phrase driver mechanisms to explain the processes which are responsible for the rapid expansion and eruption of the structure itself. And when we're thinking about the driving mechanisms, they kind of fall into 2 options. So flare reconnection that both builds and ejects the flux rope. You don't need a flux rope to be pre-existing for this driver mechanism though. And then a collection here that covers the torus instability, flux rope catastrophe, loss of equilibrium. So these are all grouped together, and there's a couple of papers here by Pascal Tiboulan, Guillaume Alanier and Bernard Kleem that discuss how these different approaches are actually equivalent and set in at sort of particular heights in the atmosphere, depending on the configuration of the magnetic field. So the point I want to make here is that even though we've got all this list of proposed trigger mechanisms, the driver mechanisms are relatively narrow. So that was a bit about the physical processes that might be happening in the run-up to a CME. Now to have a quick look at the motivations for thinking about CME forecasting lead time and what we can realistically hope to achieve. So at the moment, the forecasting of the arrival time of a coronal mass ejection is done once the coronal mass ejection is underway. Then you can get the characteristics of your CME using coronagraph data. So how fast is it propagating? If you've got stereo viewpoint, you can estimate the direction it's propagating in, and then you can propagate your CME through a solar wind model and forecast your arrival time. But given that coronal mass ejections only take, say, the fastest might take a day to reach us, the slowest might take 3 to 4 days. And then you've got to factor in that you've got to get the data down from the spacecraft. You may not have a very long lead time to be able to forecast your CME arrival. And I know certainly in the UK, it's been expressed by National Grid, who are the company responsible for the electricity distribution network in the UK, that they would like to have a 5-day forecasting lead time. So that clearly means we need to know or be able to say when a region on the sun is going to be able to erupt, because we've got to get information about the eruption before it actually takes place. So then in order to be able to achieve that, we come back to the question of what are the key physical processes that are taking place in the hours and days before the CME. and what observations do we need to identify and monitor those physical processes. So that then brings me on to the kind of core bit of my talk, which is thinking about coronal mass ejections, but thinking about this quantity known as magnetic helicity. So magnetic helicity is given by this equation. It's the volume integral of the magnetic field with the dot product of the vector potential. In words, magnetic helicity captures the complexity in the magnetic field. It captures the twist and the writhe and the linking. So it's a signed scalar quantity. It can be left-handed or right-handed, positive, negative shear. And it measures the 3D complexity of the magnetic field within a volume. And when it comes to magnetic helicity and coronal mass ejections, for over 2 decades now, there's been work looking at linking these two aspects together. Because if you have a twisted and distorted magnetic field, then you have field-aligned electric currents. And those field-aligned electric currents are a source of free energy in the magnetic field, which can be used to power the eruption. Magnetic helicity is a conserved quantity, even during reconnection events. And that has the consequence that you can build magnetic helicity across larger and larger size scales. So that also gets people thinking, well, is this cascade of helicity to larger size scales part of the process of building those eruptive structures? And I think what's been really exciting is that even though helicity as a sort of mathematical piece of research has been worked on for a long time, it was brought into solar physics through work done by Etienne, who's on the call, Pascal Dumoulin, Gerardo Valori, and many, many others over the last 20 years to help us understand how this concept can be applied in the atmosphere of the sun. And importantly, the quantity of relative magnetic helicity is used as computed for the corona, because obviously the coronal magnetic field dives below the photosphere and we don't see where that magnetic field closes. So in order to be able to make a calculation of the magnetic helicity in the corona, you need to use a reference field in comparison, and the potential magnetic field is used. And then you can use that to calculate the relative magnetic helicity within a subvolume in the corona. And that's the typical practice that takes place. So that sort of was work led by Mitch Berger, who's at the University of Exeter now. So when the kind of thinking around magnetic helicity was starting, I think the focus was very much around what impact do physical processes like coronal mass ejections or flux emergence have on the helicity evolution of an active region. And to try and illustrate that point, I've just got an active region here to show as an example. So this is the region in which we have a very simple bipole. There is convergence and shearing in the region, flux cancellation, and the formation of a flux rope, as evidenced by the sigmoid that forms in the soft X-ray data that we see in the soft X-ray data. So that sigmoid indicates magnetic field of around 1 turn, but combined, the photospheric magnetic field evolution and the plasma emission structures in the corona are absolutely in line with the Van Ballenhooy and Martin's model of flux rope formation. And a research study led by St Andrews University, so Gordon Gibb and Duncan Mackay, used Gordon's modelled magnetic field, which is driven by these observations, to calculate both the free energy in the active region, which is shown in the top right plot, just over a few days, and also the relative magnetic helicity of that region of the corona. And so the free energy increases. So we have a flux emergence phase initially, and then we have a shearing phase, and the energy is increasing. But when we look at the relative magnetic helicity, initially it has a negative sign, so left-handed, during the emergence phase. But then the photospheric flows take over and the helicity sign reverses and eventually becomes positive. And then the coronal mass ejections, there are two that take place, and they take place during this phase when the relative magnetic helicity is positive. And I think this kind of work and many others got people thinking that, well, do coronal mass ejections take place because of an accumulation of magnetic helicity in the corona? And there are certainly lots of papers that kind of toy with this idea. And it sort of feels very logical to think that. But higher magnetic helicity value does not imply more likely to erupt. So things are clearly more complicated. And I don't think there's been any work so far that has proved that coronal mass ejections occur because of some threshold of magnetic helicity value. So it's more complicated than that. So I think we're at a new phase now where we're thinking about, well, let's turn things around slightly, and let's think about what magnetic helicity can tell us about physical processes at work in the corona, not the other way around, not thinking what effect does the physical processes in the corona tell us about magnetic helicity. And that's where we come to some relatively recent work. So I mentioned about the quantity of relative magnetic helicity, which is a quantity that can be computed in the corona or from a extrapolated field or from a modelled field. Well, that relative helicity can be decomposed further. And one of the terms it can be decomposed into is associated with the current carrying parts of the magnetic field. And work led by Etienne Pariat back in 2017 suggested that the ratio of the current carrying part of the field to the relative helicity within the volume could be used as an indicator of an eruption. And this work was developed by using flux emergence simulations that showed that the ratio had a higher value when the region was going to become eruptive. So it wasn't about total amount of relative helicity, it was this ratio that seemed to be the metric that indicated whether an eruption was going to happen. And subsequently, there's been a series of papers looking at this ratio and showing great potential for its use in this way, using a series of tests on extrapolations and modelled field simulations. But the work that I want to kind of look at and then build on is a paper led by Julia Taumann, who analysed this helicity ratio, we call it the helicity proxy ratio, in extrapolated magnetic fields of two different active regions. One active region shown on the top right here, so 11158, very famous active region that was eruptive. And then another active region shown in the bottom, 12192, also very famous because even though it was large and harboured lots of flares, it wasn't an eruptive region. So Julia took a series of vector magnetic field observations of both of these regions and created nonlinear force-free field extrapolations of the corona to sort of monitor the quasi-static evolution of the corona, and from those extrapolated fields calculate the helicity ratio with a cadence of either an hour or 12 minutes, depending on the activity levels of the active region. And the findings from this study were really interesting. So the group showed that in the eruptive active region, if you plotted over time the helicity ratio, you saw that there was a big variation in the eruptive region versus the non-eruptive region that stayed with a ratio of a very low value during the time it was modelled. So the scales on here are different. So this one goes, on the left goes from 0 to 0.5 and on the right goes from 0 to 0.2. And so when you looked at the eruptions from this region, actually two are marked on here in the dashed line and the solid line, you saw an evolution and an increase in the ratio in the run up to the eruptions. Whereas there was really no evolution in the non-eruptive region. So in Julia's paper, they suggested that maybe there's a threshold in this ratio that might indicate eruptive potential of the active region. And then actually future work that's been carried out by Gupta et al. Has suggested that this threshold might be lower. So there's, I think, great potential in using this ratio, even though the details are still being worked out. So what we wanted to do was say, okay, we've got this great resource now in the extrapolations of these active regions. Let's have a look at the eruptive region, active region 11158, in more detail and see if we can start to link in that time variation of the ratio with what the photosphere is doing and what the corona is doing. So we have gone back and studied so far, so remind people this is a work in progress, the eruptive activity of this one active region, so the one on the top. So we've been looking for signatures of coronal mass ejections, so using dimmings, EUV waves, observations of eruptive structures, backed up by white light CME observations to know that it was a successful eruption. And we've been looking in general at the activity in the region. Because we want to be able to start to say, can we link the coronal evolution with changes in the helicity ratio? And then from that, elucidate which are the CME triggers, which are the important ones out of this long list that we have. So I want to show some results, preliminary results. And in order to try and kind of analyze this region in a sensible way, we have split the timeline somewhat arbitrarily into 5 different eras. So in blue, we've got phase 1, where the helicity ratio always remains below the likely or proposed threshold for eruptive activity. Then in phase 2 in green, we see a sharp rise in the helicity ratio and a kind of rounded peak, taking it above the threshold. In phase 3, again, we see another hike and a sharp peak. Phase 4, similar, starts to drop off. And then in phase 5, there is an increase again with some structure in that. And then the helicity ratio drops off. So even though this is sort of somewhat arbitrary, I think it's a useful way to kind of focus our mind. So I want to just summarize what the observations show. I don't have the details of all the observations to go through because we won't have time. So in phase 1, the helicity proxy remains below this value of 0.1, and we would conjecture then that there would be no eruptions from this region. So, and indeed, on the right-hand side, I've got the photospheric field snapshots at the start, middle, and end of this phase. So I'm sure some of you will be familiar with this active region. It was formed by the emergence of successive bipoles. So here I'm just highlighting the emergence of 3 bipoles that occurred during this phase. And the timeline of the phase ends at midnight. So the right-hand side of the plot is slightly outside of the phase. Bipole 3 starts to emerge partway through the phase. So on the plot here, the solid black line shows the helicity ratio. And on the bottom, I've got the GOES curve shown in solid and the AIA 131 light curve of the active region shown in the crosses, so that we can pick out which GOES flares are actually associated with the active region. And what we see in this phase is that there is no major evolution or activity in the corona. And there are no eruptions, there's no flaring, and the helicity proxy ratio is increasing slightly at the end of the phase, likely due to current carrying flux crossing the photosphere associated with the emergence of one of the bipoles. So then phase 2. So in phase 2, we have the rounded evolution of the helicity ratio. We have 2 new bipoles emerging into the active region, but no major flaring. And indeed, when we look at eruptive activity, there is only one eruption, but it is a failed eruption. So we see signs in the lower corona of an eruption, an expanding structure, formation of a cusp, but we don't see any white light CME to be able to enable us to confidently say there was a successful eruption. But there has been some reconfiguration of the coronal field at the same time as the helicity proxy levels off. So during phase 2, we find a failed eruption and some loop growth and reconnection in the active region at the time of the helicity proxy ratio evolution. Okay, phase 3, so this is where we see this fast rise and spike in the ratio up to its highest values. In the photosphere, we see continued emergence of flux, we start to see collision, rotation, so there's actually quite a lot of activity in the photosphere at this time that we haven't yet had the opportunity to go back and interrogate in as much detail as we need to. In terms of the helicity proxy ratio, though, we see this rising to a peak and then tailing off. There is flare activity in the active region, 2 flares, one associated with a failed eruption that's taking place as the helicity ratio is on its rise, and a successful eruption at the peak of the ratio. So the finding for this phase is that the ratio remains above this threshold value that's been proposed at all times. There is a failed eruption and then a successful eruption, and a corresponding change in the helicity ratio. Phase 4, so again we see another rise and spike in the ratio. We see continued evolution in the photosphere, rotation of polarities, motion, collision, shearing. But this time, when we look at the activity in the region, there is no successful eruption around the time of the peak in the helicity ratio. This time, what we see in the active region is jet activity. We do see in the declining phase of the ratio successful eruption, though. So there's some interesting processes happening in the corona here that again we need to look at in a bit more detail. And then phase 5, which is the final phase, and the phase in which the X-class flare took place, which was the first X-class flare of that cycle, received a lot of interest. And we're still in a phase where we are above the threshold for eruptivity. So in this phase, again, the photosphere is still evolving. We've still got shearing, rotation, orbiting motions. And now, despite the fact that there is not a very marked evolution in the helicity ratio, we see a lot of eruptive activity. So there are 4 corona mass ejections and 2 jets that take place. And you can see in the GOES plot at the bottom, significant flaring activity. So then just to kind of summarize that on one plot. So there's a lot of observational analysis gone in to sort of just a few slides. So here is the evolution of the ratio. Here is the current thinking about the threshold above which eruptivity, the active region has potential for eruptions. And then here are the times of the successful corona mass ejections, and they are all within that phase. But then in addition, we've identified 2 failed eruptions and jet activity as well. And then at the sort of tail end, there is continued jet activity in the region whilst the threshold has been exceeded. So you can see sort of at the end of the 15th and into the 16th of February, this helicity ratio declines, dips below the threshold value, but then starts to rise up again. And what we see actually is that there is no successful eruptions from this region until just after midday on the 16th of February. So broadly speaking, the eruptive activity in this region does fit with the threshold of proposed threshold in the helicity ratio. So that is really encouraging about its use for forecasting eruptions. So I think I only have a couple more slides now, and it's just sort of posing some questions about next steps, because during this last phase, phase 5, where we see lots of CME activity. We see variation in the proxy. It is above the threshold value, but there's not a kind of clear rise up to the point of the CME and fall afterwards. But maybe that's not the right way to be thinking about the use of this proxy anyway. So at the moment, we're having a think about whether there are additional metrics that need to be investigated to help with the forecasting. But one thing I do also want to stress is that there is substructure in how this proxy, this ratio is evolving, even if it is quite subtle. And this particular evolution around the time of the coronal mass ejection on the 15th of Feb that was associated with an X-class flare, I find quite interesting. Because on the one hand, you might think, well, if there was an X-class flare and a coronal mass ejection, wouldn't there be a very obvious sign in the ratio? Wouldn't it spike to quite a high value? But again, that's not necessarily the right way to think about it. But we do see structure in how it evolves. So the coronal mass ejection itself begins at about 1:40 in the morning. So that is associated with this peak. I hope you can see my cursor. And there's a bit of substructure beforehand. And what I find interesting is that from a different study I've been looking at, we can see some interesting evolution in the active region prior to its eruption. So on the left-hand side here, I've got the 94 angstrom AIA movie of this active region. So you can see there's roughly a sigmoid in the region, and it's this sigmoid that erupts. So if I fast forward it, there's the eruption and the X-class flare. But using these plasma emission structures along with the photospheric field, you can investigate A, whether a flux rate formed, and B, whether it is of the HFT type, high in the corona, or the BPS type, low down in the corona. And in this active region, using the observational signatures, it seems to be the case that a BPS flux rate formed because of flux cancellation along the inversion line. And then shortly before the eruption, at the time of this blue line, there seems to have been a transition to a HFT flux rate. The plasma emission structures in the corona change, and that's what I've used to interpret the timing and the occurrence of that transition. So this is totally tentative and speculative, but it's interesting to me that there is this rise in the helicity ratio at the time that the specific configuration of the flux rate seems to change to be one that might be more easily perturbed and erupt because of the collapse of the X line into the current sheet underneath, or perhaps related to that. So yeah, so totally tentative and speculative, but it just speaks, I think, to the potential of the research that we can do using this approach. So this is my final slide. So just to summarize, so magnetic helicity and coronal mass ejections have been a really lively topic of research for over 20 years now. And it's really exciting to me that there are still new developments that are pushing forward our approaches and our understanding about how these how eruptive events and magnetic helicity might be related, and how we might use one to learn about the other. But certainly this helicity ratio that uses the helicity of the current carrying part of the field in relation to the relative helicity in the volume has opened up a totally new way of thinking about mechanisms that lead, or processes that lead up to coronal mass ejections, and might help us with this issue of forecasting coronal mass ejections. And I also think that this ratio is opening up a new way to probe when key transitions might be happening in the run-up to coronal mass ejections. So specifically for this active region that Julia has studied in a lot of detail from the helicity point of view, and that we're now looking at from the observational point of view. So the results support the previous work that indicates a helicity ratio above a value of 0.1 indicates the potential for eruptivity. The active region is only eruptive once that value has been exceeded. And the early evolution of the active region sort of corresponds to a time where there's a more marked variation in the ratio. The ratio seems to be less sensitive to changes once major activity has started. And so we need to look more into why that's the case. So this is very much work in progress, but I hope it sort of raises knowledge and awareness of what's happening in the work of helicity at the moment and the potential of what we can do in the future. So I'll say thank you for listening, and I think we've still got time for questions.